So last time we were discussing about motion along a straight line or kinematics in one dimension, and we came to the special case of uniformly accelerated 1D motion. So let's continue with that today. Understand some applications and examples of that. So we have seen the derivations of these three equations. V equal to U plus AT. S is equal to UT plus half AT square, and V square is equal to U square plus 2AS. The so-called three equations of motion. Now let's start today by understanding some of the graphs. So velocity versus time graphs. So case one where U and A are both positive. That means they are in the same direction. So in this situation, the graph of velocity versus time will look like a straight line with a positive slope. So this point here will be U, and also the slope of this. At some time t, the velocity is becoming some particular value v. And you can see that the slope, which is that is equal to the uniform acceleration a, and the slope of tangent at any particular point is also a. So it has a positive slope. Whereas if we talk about the second case, where U and A are in opposite direction, so U is, let's say, positive and A is negative. In that case, the velocity time graph will again look like a straight line, but with a negative slope. This slope or tan theta will be a negative quantity. Whereas here it was positive. Okay, so make a quick note of this, then we'll discuss more.
So can you explain case 2?
Sorry, what was the question again?
So can you explain the case 2 in opposite direction?
But I'm not able to hear you clearly. Your voice is breaking. Can you send me the question in the text message otherwise?
Sir A is asking to explain case 2.
Case 2, the acceleration is negative. So the slope of the straight line is a negative quantity. So as you can see, with time increasing, the velocity is decreasing.
The same with theta on the other side.
Please speak a little louder, but I'm not able to understand what you're saying.
Shouldn't theta be on the other side, left side?
No, theta is always taken as the angle with respect to the positive x-axis. You have done equation of straight line in mathematics, so you're aware of that.
Yeah.
Tan theta is positive when theta is acute because it has a positive slope. Okay, whereas tan theta is negative when theta is obtuse because it has a negative slope. You always take theta as the anti-clockwise angle with respect to the positive x-axis. Okay, so let's look at an example question based on this concept now. Sometimes the information in the question can be given to us in the graphical form. So given is the velocity time graph for a one-dimensional motion. 1D motion means one-dimensional, a motion along a straight line. So velocity is in meters per second. The time is in seconds.
The second case में theta कौन सा था?
Come again?
In second case, what was theta? In second.
Theta is the angle made with the x-axis. You know why you people are having confusion with this? Any straight line, whether it has a positive slope or a negative slope, whatever angle it makes with the x-axis, tan of that angle is called the slope. Tan theta is y2 minus y1 upon x2 minus x1. You have done this repeatedly in coordinate geometry many times. We discussed this in calculus also many times. This is called the m, or the slope of the straight line, y equal to mx plus c. So in this particular case, you can see theta being obtuse, m is negative, the slope is negative. In this case, you can see theta being acute, m is positive, it has a positive slope. Is it clear now?
Yes, yes.
Okay, so let's come back to this question. So this is the information given in the question, that at 0, the velocity is, let's say, 60 meters per second, and it reduces to 50 in a time of 2 seconds. So this is a uniformly decelerated motion. Starting at t equal to 0 with u equal to 60 meters per second, and until it stops at t equal to capital T. So what we have to find from this information now is, I mean, this given graph, what we have to find is the acceleration, okay, to find the value of this total time and the total displacement, that is from 0 to t. Okay, so just work this out quickly. Okay, Sumit, Parv and Anand, your answers are correct. Very good. Akshat, correct. Parv, your third answer is also correct. Good. Siddharth, your answer is correct. Very good. Akshat, your answer is correct. Very good. Adinath, correct. Okay, so we will discuss a couple of different approaches of doing this type of question. So the first is the formula-based method. Formula-based method. You can see that it is a case where acceleration is uniform because VT graph is a straight line. So the moment the velocity time graph is a straight line, we know that acceleration is uniform. So we have the formula V equal to U plus 80. Okay, so now in this you can see that U is equal to 60. This is one information that is known, and V is equal to 50 meters per second at t equal to 2 seconds. This is one more information that is known. So from this now we can substitute. So substitute this here. So you can get the information that 50 is equal to 60 plus a into 2. So from this immediately we can see a is minus 5 meters per second square. And the fact that it is negative, you can see that because the straight line had a slope, it was negative, which means that the acceleration is negative. So that works out okay. And we have the relation that now we want to find that time this. So again we substitute this, that 0 is equal to 60 plus minus 5 into capital T. So from this we can see that that time is 12 seconds. Okay. And then we all calculate the displacement from 0 to t seconds. So we have two methods. We can go with, or we can go with, so 0 square is equal to 60 square plus 2 into minus 5 into s. We'll go with this, or s is equal to 60 into 12 plus half into minus 5 into 12 square. So both options are there for us.
Sir,
Yes.
so you thought once that
Yes, what
displacement
happened?
is likely to area of the graph.
Say a little louder, but I can't hear you again. Your voice is not coming clearly.
You thought of that displacement is also the area of the graph.
Yeah, you can. So that is a graphical method. So I'm coming to that also. This first thing that the first method that I'm discussing here is the formula based method. Okay, so that's not the only method of solving the question. You can also use graph, and from the graph you will, like you said, the displacement will come from the area, the acceleration will come from the slope. Such things we can do. Okay. But we can also, just plug in the information from the graph in the formula based approach and just simply solve it by making use of the formula that we already know. Okay. Okay, so hope this method is clear to all of you. If there's any doubt, please let me know. Now the second is we can just also use the graphical approach. So in the graph based method, we know that since acceleration is dv by dt, so therefore acceleration is the slope of the velocity time graph. And since velocity is rate of change of displacement, so displacement is integration of v dt. Okay, so that means displacement is the area under the vt graph. Okay. So you can make use of this information and this information and solve it completely without using any formula or anything, but just by using this concept. So Since our graph was like this was 60 and this became 50 after 2 seconds. So you can see the slope. So it is 50 minus 60 upon 2 minus 0. That's see that. And also to find this time t, 0 minus 60 upon t minus 0 should be equal to a. So minus 60 by t should be equal to minus 5. So that time is 12 seconds. And then the total displacement will just be the total area of the triangle. So it's this total area. Base into height. Okay. So these are the two different approaches by which we can solve any problem of this type. It's really a matter of choice which approach you want to go for. It's not that one method is particularly faster than the other in this kind of situation. You can go for the graph method, you can go for the formula method. You should know both the methods. Okay, so hope this question was fully clear. Now let's use this data of this question, or maybe a fresh question, but in a different way. Another type of example is, suppose this is given to us that a particle starts at t equal to 0 with initial velocity. This time let's take something different, maybe 20 meters per second along a straight line with a uniform acceleration in the opposite direction of k equal to minus 2 meters per second square. So first thing we want to do here is plot the v versus time graph. Second, find the instantaneous velocity at t equal to 8 seconds, t equal to 10 seconds, t equal to 12 seconds, and find the displacement from t equal to 0 to 8 seconds, 0 to 12 seconds, 8 to 12 seconds. Now we'll also do one more thing. We will calculate the distance traveled in the same 3 intervals of time. So start this question.
Sir,
Yeah,
both B and C parts are 12 seconds.
B and C parts. No, but see, one is 0 to 12 and C part is 8 to 12 seconds. Huh?
Yes.
Understood? The interval is different. The final time is the same. So let's check out the answers for this. So first of all, once again, our velocity time graph will look like a straight line with a negative slope. And this time you notice that because we are talking about a time of up to 12 seconds even, so the velocity is going to go to a stage where it becomes negative. You would have realized that by calculating the second and third part and all that, that it's not just a case of the velocity going to zero. It starts from 20 meters per second and the slope is minus 2 meters per second square. So in 10 seconds, the velocity becomes zero. So obviously in 12 seconds, the velocity has reached a negative value of in fact minus 4. Whereas in 8 seconds, it would have had a value of plus 4. So this you will understand by substituting the values in the equations and all. So this is our velocity time graph in meters per second versus seconds. So instantaneous velocity is, you can use the formula 20 minus 2t in this case. So at 8 seconds, you can see it will become at 10 seconds, it will become 0. And at 12 seconds, it will become minus 2 meters per second. Sorry, minus 4 by mistake. So hope all of you understood that part. Most of you got these answers correct. Now for displacement, we can go by two methods. We can either go by formula, that is S is equal to ut plus half at square, or area under graph method. So if I go by the formula method, let's see, displacement after 8 seconds. So displacement will be 20t minus t square. So 160 minus 64, so 96 meters. Displacement after 12 seconds. So that is also coming out to be 96 meters. Okay. And that shows you that what is happening is that the displacement from 8 to 12 seconds should be 0. Okay, now I'll show you the area-based method also in just a moment. So this is happening because the object is actually going up to a maximum displacement and then returning back. When the velocity becomes negative, the object is returning back. So that is why between 8 and 12 seconds, the net displacement is 0. Because whatever forward displacement it covers, it retraces that displacement coming backwards with a negative velocity. Now also think carefully about how you will calculate the distance, because you know the difference between distance and displacement. Distance is not a vector quantity, it is just the scalar path length. So now you think carefully about how you will answer the last part of the question.
Since it is a uniform motion, displacement will be the distance only.
No. Direction can change now. One-dimensional motion. It has a negative acceleration. So at some point of time, if the direction is reversing, it's going from positive to negative. Yeah. So then
we can apply the Pythagoras theorem. So we can apply the Pythagoras theorem
Pythagoras from what for beta? There is
for the
nothing
distance.
related. No, but the path is not along the hypotenuse of a triangle. Now the path is straight line. So why you will use anything to do with triangle? You understanding my point? Na? Try to visualize how the motion is happening. Na? It's along a straight line only. Okay, so this is where the whole graph thing also becomes very useful. Okay, because it shows us at what point of time the direction of motion is changing. Na? So in the interpretation of this graph, you can understand that the motion is happening in the positive direction up to 10 seconds. Okay, so what is happening that from t equal to 0 to 10 seconds, the velocity is positive but decreasing in magnitude. Okay. So it is having a decelerated motion in the positive direction. Then exactly at t equal to 10 seconds, v is 0. So it stops for a moment. It does not remain at rest. Okay, because next moment the velocity is becoming negative. And by moment we don't mean second, just we mean an instant of time. Okay. And from t equal to greater than 10 seconds onwards, the velocity is negative. That means it's moving backwards. Okay. And that too with increasing speed. So that means it's an accelerated motion. Okay. So if you visualize the motion of that particle now, you'll realize that suppose it started from here at t equal to 0 with an initial velocity of 20 meters per second. Okay. Then going in this direction, somewhere along the line, let's say at t equal to 8 seconds, it's here. Its velocity has become less, it's become only 4 meters per second. So like that now, it comes to a stage where it's reached the limit. It's momentarily stopped because it was decelerating. So it's just stopped for an instant at 10 seconds. But after that, what's happening is going backwards. It crosses this point again, but at 12 seconds. And this time with a velocity of minus 4 meters per second. So in my diagram, the arrow is showing that it's in the opposite direction. So now you can see that from here to here, what is the total distance? This distance is how much we need to calculate. So from 0 to 10 seconds, if we use this relation, you can see that 0 square is equal to 20 square plus 2 into minus 2 into s. So this displacement is 400 divided by 4. No? So it's 100 meters. So this distance is 100 meters. Okay. Whereas up to 8 seconds and then again at 12 seconds, what is this distance from the starting point? It's 96 meters. We've calculated that before. So we can see that 0 to 10 seconds, it's going 100 meters in the positive direction. Okay. Then from 10 to 12 seconds, what's happening? It's going how much? It's coming back 4 meters, but in the negative direction, in the opposite direction. That's why the displacement from 0 to 12 seconds, it had come out to be how much? It had come out to be 100 minus 4 or 96 meters. By formula also it had come out like this. But the distance, I talk about the distance from 0 to 12, it should become 100 plus mod of minus 4. So it should become 104 meters. So in that 0 to 12 second interval, the distance traveled is this much. Similarly, the displacement from 8 to 12 seconds was 0, but the distance from 8 to 12 will be what? The distance from 8 to 10 plus the distance from 10 to 12. So this is 4 meters only, but this is minus 4 displacement, so mod of minus 4. So it's traveling 8 meters distance in those 4 seconds, 8 to 12 seconds. Okay. So for this visualization of the motion and to understand the difference between distance and displacement, again, your velocity time graph comes very useful because it shows you which part of the time interval the direction is positive, which part of the time interval the direction is negative. So for example, if you're talking about the total 12 seconds, 0 to 12 seconds, this graph shows you that I have to break up the motion into two parts, 0 to 10 and then 10 to 12, because at 10 seconds, this direction is switching. So without that knowledge that at what time the direction is switching, I will not know how to calculate the distance now. Right, but so your approach is correct. So hope you got the same answer using this approach. Okay. Some of you got the correct answer, very good. Yes, Siddharth, your answers were correct.
Sir, from 8 to Sir, what about from 8 to 12 seconds?
It's coming, it's below over here. Okay, I'm just sending you the answer. The answer is 8 meters. Okay, you can figure it out by the same kind of method, try it out yourself. So 8 to 12 also what I'll have to do now, I have to break the motion into two parts. 8 to 10 is going in the forward direction and then 10 to 12 is coming in the backward direction. So I'll just need to understand like how to divide that motion, correct? Okay, so hope this is clear. I'm just taking you through the last part, which is the distance traveled from 8 to 12 seconds. That's calculated over here.
Sir, while taking a displacement from 8 to 12, what we
Yes.
consider as T?
No, we didn't need all that, no, because we knew the displacement from 0 to 8 seconds. We had calculated earlier. No? See, we saw the displacement at 8 seconds was 96. So this is basically what it is from 0 to 8 seconds. No? And then we saw again the displacement at 12 seconds was also 96. So now what about the displacement from 8 to 12? It is the displacement after 12 seconds minus the displacement after 8 seconds. So that's how we got it as 0.
Okay, sir.
Understood now?
So,
Okay,
sir,
now we can also.
basically when we have two time limits, and we have to first find the displacement from the T2, then from T1, and then subtract it.
Yes, yes, that will be the correct approach to it. Okay, or otherwise we can always do the graph approach. Okay, so I'm coming to that also. Now in the graph approach, you just have to use the proper formula for area. So velocity time graph. Now we can see that, for example, if we want to calculate the displacement from 0 to 12, what we'll have to do is we'll have to subtract the area of these two triangles. Why subtract? Because displacement has sign. So because displacement has sign, so this area will be counted with plus sign, this area will be counted with minus sign. So if this area is A1, this area is A2. So the displacement from 0 to 12 will be actually A1 minus A2. But the distance will not be with minus sign. The distance will be mod. Okay. So it won't be plus of A1, it will just be A1 plus A2. Okay. So you can see that this area is half of 10 into 20, so it's 100. And this area, because this was coming out to be minus 4. Okay. So you can see that this height is 4 and this base is 2. So this is okay. So it's 96, whereas this will just come out to be 104 meters. Okay. Similarly, now you can see that here our 8 seconds is at this point of time over here where the velocity is becoming. So we think of this area as an A prime. So the displacement from 8 to 12 seconds is back actually plus of A prime minus of A2. So that when you calculate, you'll see it will come out to be plus 4, minus 4 or 0. But if you talk about the distance, then we have to just take the magnitude of the two areas and add them. So it's just A prime plus of A2. So it will come out to be 8 meters. Okay, so this would be the other approach. This would be the graph-based approach. Solving the same thing. Area under the graph method. All right, so hope both the approaches are clear to all of you. Now we move on to the next thing in terms of graph. You will see the displacement versus time graph. Okay. In a uniformly accelerated one-dimensional motion. So we know that the relationship between displacement and time is given by this, that S is equal to ut plus half at square. So we can see that displacement is a quadratic function. It is a polynomial with degree 2. So it is a quadratic function of time t. So in general, we know that the graph should be what type of graph? It should be parabolic. We've learned about this before also. So now again, there are two cases when U and A are both positive. Okay. So it has increasing velocity. This time, let's draw the graph with an example of. So let's take an example of, let's say, U is equal to 20 meters per second, but A is equal to plus 2 meters per second square. So our displacement as a function of time will become 20t plus t square. So now from our knowledge of graphs and calculus, we will understand, and I'll illustrate in more detail also, but you'll realize that the graph of displacement versus time, remember it's a time graph, so we will not take the negative side of the axis. Time will start from 0 only. So this graph will look like this. It will look like something like this. So you can see the slope is increasing. The slope is increasing because the slope is nothing but the instantaneous velocity. So that is increasing. Okay. So for example, if we use this formula, we can see that at t equal to 1 second, how much the displacement is according to the formula. You can see it is 21 meters. Okay. But at t equal to 2 seconds, the displacement would have become how much? 40 plus 4. So it's 44. You can see definitely it's not a linear kind of graph because it's covering more and more displacement in every 1 second interval. Now where this graph comes from, it comes from, if you were to look at the graph of y is equal to 20x plus x squared, this kind of graph. So you would see that it's a parabola like this. If you factorize it, it is 20 plus x. So its roots, that is y is equal to 0 at x equal to 0 and minus 20. And if you differentiate it, dy by dx is equal to 20 plus 2x. So you can see that its vertex, that is the local minima point, is at x equal to minus 10 because dy by dx is 0 at that point. So the general graph of this parabolic function or this quadratic function would look like this. But here we are not plotting y versus x, we are plotting s versus t. So we'll only take the positive side of the time axis. Okay, so it would be like this. The vertex would have been at the point minus 10. This other root would have been at minus 20. But here it's not this function. Here the domain of the function was all real numbers. But here we're talking about a time function. So the domain is only for time greater than equal to 0. So only this part of the graph comes in. Only this part of the graph where x is greater than 0. So that's why for us, only this part of the graph is significant. Okay. So it's like one section of a parabola. And that section is this one, which I've drawn over here. Okay. So please analyze this graph carefully. Okay. And note down the important points over here. Then we'll look at the second case where A is negative and U is positive. Okay, people, so hope this is clear. Now moving on to the second case, where our initial velocity is positive, but our uniform acceleration is a negative quantity. Okay. So V is decreasing with time. So that kind of graph. Okay. So for example, let's take U as this time maybe plus 10, and let's take A as again minus 2 instead of plus 2. So we have S is equal to 10t minus t square. So what this particular time graph will look like? It will look like a parabola, but which has a downward pointing parabola. So displacement in meters and time in seconds. This time let's plot the general graph first. Suppose we have y is equal to 10x minus x square. So one thing we can see is the roots of the equation. Y is equal to 0 implies that x into 10 minus x is equal to 0. So it's 0 and 10. These are the roots. And the second is we can see the vertex, or in this case, it will be the local maxima point because it's a downward opening parabola. So at that point, dy by dx should be 0. So dy by dx is how much? 10 minus 2x. That should be 0. So x equal to 5. This is the vertex point. Okay. So in general, how the graph of this one will look like? It has two roots. Sorry. It has 0 as the root and x equal to 10 as the root. And the parabola is shaped like this. This vertex point will be 5, at which we will have the local maximum. So accordingly, now we have to take that portion of the graph which is for positive domain or non-negative domain. So our s versus t graph will look like this. Might even go beyond this point. Displacement can become negative because it can go past where it started from. So this will be 5 seconds. This will be 10 seconds. And one more thing we can just do to get a guideline over here, keep track of things, is also how the velocity versus time graph is looking. And from that, we'll realize there's a correlation between these two things. If we look at the velocity versus time graph, it is 10 minus 2t. Okay. So that would be a straight line like this. Like this. Okay. So what we would see is that starts from 10 meters per second because the acceleration is minus 2. So this would be 5. And then we also see that at 10 seconds, this would become minus 10. Okay, and which would also show us that the total area as a displacement would become 0, which is what the displacement time graph is also showing. Okay. So first of all, the displacement time graph is a downward opening parabola. Its slope, that is ds by dt equal to v, is positive and decreasing from 0 to 5 seconds, which is what this is also showing you, that velocity is positive and decreasing from 0 to 5 seconds. Okay. And the slope is negative after 5 seconds. That means v is negative and mod v is increasing. That same thing you can see here also, that after 5 seconds, the velocity becomes negative. Okay. So that's one point. And we'll also discuss about the 10-second instant of time, which is very significant because the displacement is becoming 0 at 10 seconds. So it's come back to where it started from, which is the same thing that this area will also show you. That this area and this area between 0 and 5 and then 5 and 10, the two areas with their algebraic signs will cancel each other. So that will show you that your net displacement is 0. So the distance traveled is not 0, but the displacement is 0. Graph is also showing that the displacement was increasing up to 5 seconds. And then after 5 seconds, the velocity has become negative. So the displacement again starts decreasing. And finally, it becomes 0. That means it's come back to the starting point at which instant of time at 10 seconds. So all this information which we are talking about, it's very nicely represented in the two graphs. Okay, and also there is a nice correlation between the two graphs, which we have noted part of. Okay. So just make a thorough analysis of this information and note down the key things. Let me know if there is any doubt. Okay, so the second point that we want to understand here is the significance of that 10-second instant of time. At t equal to 10 seconds, the net displacement is again coming out to 0 because the particle has retraced its path. Retraced means it's just traced back, come back like a mirror image along the same path that it went. Okay. And return to the start point. Okay. You can also see in this graph the area algebraic sign included. So the area from 0 to 10 seconds is 0. So the displacement from 0 to 10 seconds is 0. Okay, so this is about the two types of displacement time graphs that we get, depending on whether the acceleration and velocity have the same, I mean, u and a have the same sign or u and a have opposite sign.
Sir,
Now, yes.
sir, after the 10 seconds, the object starts moving in the opposite direction from the starting point.
Yeah, I mean, not only it's already moving in the opposite direction, okay, from 5 seconds onwards to the starting, but what is happening is it's gone past. So if the object started from here at t equal to 0 with a velocity of 20 meters per second, so then it's gone like this up to 5 seconds. Is going in this direction, but the velocity has just become 0 for a moment. Now after 5 seconds, it starts coming back like this. So let's say it's 6 seconds or something. It's over here again, but having a negative velocity. Okay. So like that, it's returned back here exactly at this point. At what time? 10 seconds. So the displacement is 0. But now what's happening after 10 seconds? So for example, at 12 seconds, it's here. So its net displacement has become negative. Okay. So it's net displacement. So you can see that, and for t greater than 10 seconds, the net displacement becomes negative. So its displacement is in the negative direction compared to where it had started its motion from. Understood this point now? Why this s is going in the negative direction?
Yes, sir.
Okay. It's basically gone past where it started from in the opposite direction. Okay, now just a couple of more interesting aspects related to this motion with uniform acceleration. So two other important equations, okay, or two other formulae. Average velocity in a uniformly accelerated.
Sir, sir,
Yes.
if both are negative, then also they will have upward opening parabola, na?
See, both are negative means, we can do one thing. We can take our axis only in the opposite direction. Why we want to take two negative things? You understanding my point? Na?
Okay, sir.
I mean, we can keep it negative, but then we'll have to draw the graph like this. If u is also negative and a is also negative, then our velocity time graph will look like this. Our velocity will be on the negative side now. So our velocity time graph will look like this. It starts with some negative value, let's say -10, and after some time it's become an even larger negative value after, let's say, 5 seconds or whatever. So instead of this, what we will do is we'll just reverse our axis now, so that both become positive. So our s versus t graph in this case will look like this. It will look like this, because s would be equal to, like, let's say -10t minus t square or something like this. So it will look like this. So it will look like a mirror image of that graph where it was 10t plus t square. So in that sense, these two graphs are not different. They have the same behavior. Okay, so that's why we are not taking those cases separately. You understand?
Yes. Sir.
Now, average velocity in the case of a uniformly accelerated motion. So, for example, from t equal to 0 to t equal to t, the average velocity should be what? It should be total displacement upon total time. So it is ut plus half at square upon t. So you can see it is u plus half at. Now we can write this as 2u plus at, the whole thing divided by 2, which we can further write as u plus at, the whole thing divided by 2. So you can see we can write it as u plus v by 2. So the average velocity from a time 0 to a time t actually becomes the arithmetic mean of the initial and final velocity. That's one thing. The other thing is that if we want to calculate average velocity from some time t equal to t1 to time t equal to t2. Okay, so now let's say at t1, the velocity v1, that's how much u plus 8t1. And at t2, the velocity v2 is equal to u plus 8t2. So in this time interval, the average velocity from t1 to t2 will actually become v1 plus v2 by 2. There's a similar proof for this also, like the one I've done above. Okay, and I'll show it, but I'll show it by the graph method. So whether we are looking at average velocity from 0 to some time t, or we are looking at average velocity for some intermediate time, like 1 to 5 seconds, or 7 to 8 seconds, or something like that, t1 to t2, the average velocity will be always the arithmetic mean of the velocity at the beginning of the interval with the velocity at the end of the interval. So make a note of this. So here how we define average velocity would be that it would be the displacement from t1 to t2 divided by the time interval. So when I calculate this quantity, it will come out to be this one. So this is also a very useful concept to keep in mind. Sometimes we can use it in place of the standard 3 equations to solve something faster.
So can you explain the second one again?
Yeah, so I'll explain to you the method for the second one by the graphical approach. But you can also try the proof yourself by the formula approach that show that the displacement from time t1 to t2 divided by the time interval can be shown to be v1 plus v2 by 2. Okay. So my velocity time graph for a uniformly accelerated situation will be a straight line. Now, just for reference, I'm taking positive slope. It could have been a negative slope also. Now, supposing I want to calculate the average velocity between this time here t1 and this time here t2. So in terms of graph, okay, so if the velocity here is v1, the velocity at this point of time is v2. So in terms of graph, tell me what is the displacement from time t1 to t2? How will I calculate the displacement from the graph? Will be this area?
Area of parallelogram. Trapezium.
Trapezium. So I'll have to calculate the area of the trapezium. So area of trapezium, what is the formula?
Half into length of parallel sides into height.
Yes. So it will be area of trapezium. Okay. So tell me how much are the parallel sides here? They are V1 and V2.
V1 and V2.
And what is the distance between them?
T2
This is
minus
that perspective. So it's T2 minus T1. So into T2 minus T1. So this is the displacement from time T1 to T2. So now what about the average velocity from T1 to T2? It is equal to the displacement from T1 to T2 divided by the time interval, that is T2 minus T1. Okay, so it's coming out to be half V1 plus V2. It's coming out to be the arithmetic mean of these two. So I've shown it to you by the area under the graph method. You can also get it by the formula method. Okay, but more important is to remember the concept that in a given time interval, if I want to calculate the average velocity, all I need is the velocity at the beginning of the time interval V1 and the velocity at the end of the time interval V2, and I need to calculate the mean of those two, that is the arithmetic mean V1 plus V2 by 2. So this can be used as a very effective trick in certain type of problems also. I'll show you. Now, for example, if I have a problem like this, that a particle moves with uniform deceleration along a straight line, such that at t equal to, let's say, 10 seconds, its velocity is equal to, let's say, or t1 equal to 10 seconds, its velocity v1 is, let's say, 25 meters per second, and t2 equal to 20 seconds, its velocity, say, v2 is equal to 35 meters per second. So we want to calculate, find its displacement from t equal to 10 to 20 seconds. So this t1 to t2 only, we want to find the displacement. Now normally how we do this question, if we went by the absolute formula based approach, we would have said that, okay, v is equal to u plus at. So v1 is equal to u plus at1. So when we substitute this, we would have got 25 is equal to u plus 10a. Okay, and v2 is equal to u plus 82. So that would have given me that 35 is equal to u plus 20a. So from this, I would have calculated how much a is and how much u is. Okay. And then I would have seen that, okay, s is equal to ut plus half at square. So I would have calculated s1 as ut1 plus half at1 square. I would have calculated s2 as ut2 plus half at2 square. Then I would have calculated s from 1 to 2 as 2 minus s1. So very lengthy process, as you can see. Okay. But if I go by the trick, okay, use the average velocity concept. You can see how this question can be done in one line. At t1 equal to, what is it, 10 seconds, my v1 is given to me as 25 meters per second. Okay. At t2 equal to 20 seconds, my v2 is given to me, oh sorry, this is a uniform acceleration then, because I've taken 35. So it's a uniformly accelerated motion. Anyhow, it will work if it were a deceleration also, as long as it's uniform. So what I can now say is that between 10 to 20 seconds, the average velocity is v1 plus v2 by 2. So how much that is? That is 30 meters per second, correct? Okay. So therefore, the displacement from 10 to 20 seconds will become the average velocity into time. So that is the definition of average velocity, that is displacement upon time. So the displacement from 10 to 20 seconds should be equal to nothing but the average velocity of 30 meters per second into the time, which is 10 seconds. So it should be 300 meters. So in one line, the question is done. You can just check out these two values and see, okay, the average velocity is 30 and the time interval is 10 seconds. So what is the displacement? It's the average velocity into time. So it's 30 into 10 is 300 meters. Okay. I'll also verify this for you with the formula-based method, and we'll also understand this graphically, but you will see that how this approach gives you a distinct advantage in this type of question. It becomes a very nice shortcut trick for doing questions where some two random instants of time are given to you and the velocities are given at those two instants. You want to calculate either directly average velocity or displacement or something like that. You can always use this trick. Okay, so let's complete it by this method also. So using this equation and this equation, you can see that if you just, for example, subtract them. So on this side, you get 10 is equal to 10e. So we get e is equal to 1. Okay. And from that, we will get u as how much? 15. So now using these two values, you will get S1 as how much? We'll get 15 into 10 plus half into 1 into 10 square. And we get S2 as 15 into 20 plus half into 1 into 20 square. So that will give us 150 plus 50. So that's 200. And this will give us 300 plus 100. So 400. Oh, 500. So 400 by 2. So 400. So that gives us 500. Okay. So now you can see that the displacement from 10 to 20 seconds is going to be S2 minus S1. So it's 300 meters. Okay, so you're getting the same information, but after a lot of effort, in comparison to this. Okay, so hope this question is clear, people. Now, another very useful little trick and formula is a direct formula for displacement in the nth second of motion. So first, let's understand what this statement means. So nth second, what does that mean? So if the motion starts at t equal to 0, okay, then the interval of time from t equal to 0 to t equal to 1 second, this interval is called the first second of motion. There's a difference between saying t equal to 1 second and saying first second of motion. So first second of motion is an entire interval of time of 1 second, but from when to when? 0 to 1 second. Similarly, from t equal to 1 second to t equal to 2 second, that's again a 1 second interval, but it's the second of motion. Okay. Similarly, from t equal to 2 seconds to t equal to 3 seconds, this is the third second of motion. So like that, in general, from t equal to n minus 1 seconds to t equal to n seconds, that interval of time is called the nth second of motion. So now we want to talk about displacement during the nth second. So that should be basically what? It should be displacement after n seconds minus displacement after n minus 1 seconds. So from 0 to n seconds, the displacement is how much? It is nu plus half an square using the formula s is equal to ut plus half at square. Similarly, from 0 to n minus 1 seconds, what is the displacement? It is n minus 1 u plus half a into n minus 1 square. So now from this we will calculate by subtracting these two the displacement during the nth second. It is the displacement after n seconds minus the displacement after n minus 1 seconds. So that will become, when you subtract these two, you see it will become u plus half a into 2n minus 1. So this is a useful little formula in itself for certain types of problems. We'll discuss in just a moment. First, write down the meaning of this statement itself, what we mean by displacement in the nth second, and then the derivation of this formula. Yes, Sumit, to answer your question, it is possible to do that earlier question by using a graph also. You just draw a straight line graph, and in that graph, you would have those data points that at whatever t equal to 10 seconds, the velocity was 25, and at 20 seconds, it became 35. So then you would calculate the area of that trapezium between those two times as the displacement and divide that by the time. That would be the average velocity. Or in this case, you were calculating the displacement directly. So the displacement would be just the area under the trapezium. So that would also be a very fast way of solving. Always graphical analysis in kinematics gives you a very nice option of solving problems. Okay.
Yes, sir.
Okay, so let's see an example now. Suppose we have some information given like this, that u is equal to 20 meters per second and the acceleration is equal to, let's say, plus 4 meters per second square. We want to find the displacement in the 5th second of motion. Or sometimes we have also an interesting question of this type, that find the ratio of displacements in, let's say, the 5th second is to displacement in . let's say the 6th second. So since it has a positive acceleration, so obviously with each second, the displacement will go on increasing. So this ratio should be less than 1. But anyhow, so let's see. So instead of using the whole thing, you know, that, okay, S is equal to ut plus half at square. So that in this case is 20t plus 2t square. So displacement after 4 seconds is 80 plus 32. So it's 112. Okay. Displacement after 5 seconds is 100 plus 50. That's 150 meters. So the displacement in the 5th second is displacement after 5 seconds minus displacement after 4 seconds. So it is 38 meters. So instead of doing this, we can now just go with the direct formula based method. Displacement during the nth second is just given by the formula u plus half a into 2n minus 1. So displacement in the 5th second here will be u, which is 20, plus half into a, which is 4, into 2n minus 1. So that's 10 minus 1 on 9. So it is 20 plus 18, so directly 38 meters. Like that, you can see that the displacement during the 6th second will be 20 plus half into 4 into 2n, that is 12 minus 1, so 11. So it is 20 plus, what is it now? 22, is it? So it's 42 meters. So the ratio of the displacement in the 5th second is to the displacement in the 6th second, become 38 is to 42, or 19 is to 20. So these type of specific questions which are related to the nth second displacement, they have to be approached by this particular method. Okay. I mean, ideally they should be approached by this formula. You always have the fundamentals to come back on, so you can come back to these relations like I've done on the left hand side over here, but that will take more time. That's why this shortcut formula helps a lot for displacement in the nth second. So we've covered a lot of ground today in application of various types of situations and formulae and graphical method and all that for the special case of uniformly accelerated one-dimensional motion. So this covers every aspect of uniformly accelerated one-dimensional motion. Okay. So in the next lecture, we will be looking at a special case of 1D motion with uniform acceleration, which is vertical motion. That is either free fall of an object when you drop an object from a height, or you might even throw it down, so it's in free fall under gravity, or in case of vertical projection, that is you throw up something but with a vertical velocity, so it goes up and comes down. So those two situations together, vertical motion under gravity, so that is a special case of uniformly accelerated 1D motion. So we look at that, and from there we will move on to projectile motion, which will be our first case of 2-dimensional motion. Okay. Motion in a plane.
Plus, it means that in the major test 3 we have 1D, so we have to do
You
for
will have
gravitation also, right?
Yes, it will include vertical motion, which we'll be discussing in the next lecture, right?
Okay, sir.
In the meantime, you can get started with questions from HC Verma as well as the module. I will send you a list of questions plus a worksheet on 1D motion. Okay. So you can do that in the next 5-6 days so that we can discuss the doubts in the next lecture. Okay, so that's it for today's session, people. Thanks for attending and wish you all the best.
Thank you, sir.
Thank you.
Yes, sir.
Thank you, sir.
Okay, bye, people.